Hello everyone. How are you doing today? Hope all of you are doing well. Here I am, dear Sharma, bringing you contents of physics through our YouTube channel, Science Informatics. I was presenting applications of Ampere's circuital law. I have already presented one application, that is magnetic field due to a straight conductor. I want to remind you some of the important points in this topic. How to use Ampere's circuital law to find the magnetic field at any point. The first step is to find the direction of current and shape of current. Then choose the proper Amperian loop. Then calculate line integral and use the statement of Ampere's circuital law, which states that the line integral of magnetic field around a closed loop is equal to mu naught times the total current enclosed by that loop. Mu naught is the permeability of free space. I is the total current enclosed by the closed loop. In this case, we have found the magnetic field due to a straight conductor. You must remember that the magnetic field lines due to a straight current carrying conductor are the concentric circles around it with that conductor as axis. So we have chosen circular Amperian loop passing through the field point. Field point means the point where we are going to calculate magnetic field. In this case, the Amperian loop is the circle, whose points are equidistant from the conductor. So magnetic field is constant throughout this circle. And the direction of magnetic field in this circle is along the tangent at any point considered. And the direction can be known by using right-hand thumb rule or right-hand screw rule. In this case, the current is upward, as you can see here. So if you use right-hand thumb rule, the direction of magnetic field at any point, say point P, is along the tangent that is shown by red line arrow. And at every point on this circle, the direction of small elemental length dl is always along the tangent and in the same direction as B. So B dot dl becomes equal to BDL this way because angle between B and DL is 0, cos 0 is 1. And then line integral becomes equal to B times 2 pi r. We used Ampere's law, then found the expression for magnetic field B equal to mu naught I by 2 pi r for the very long straight conductor. As the constant current is passed through that conductor, magnetic field is inversely proportional to the distance from the conductor. This is hyperbolic variation. So graph of V against R would be hyperbolic curve as shown in figure 2. Okay. Now let's go to second application of Ampere's circuital law. Here, magnetic field inside a long solenoid, actually infinitely long solenoid. We have considered this case. Solenoid is a helical winding of insulated copper wire wound on a cylindrical frame, usually of circular cross section. A current carrying solenoid is represented as shown in this figure 2. Okay, let me point it. Yeah, this is representation with the direction of current. The cross here means the current is flowing into the plane of paper, and dots means the current is coming out of the plane of paper at that point. So in this case, we have taken the direction of current to be clockwise on the right end, and on the left end it is anti-clockwise. So the direction of magnetic field is from right to left. And as you know, the magnetic field inside a solenoid is uniform, so they are represented by parallel lines. Now, to apply Ampere's circuital law, we have to choose a field point. Say we are going to calculate magnetic field at point P inside the solenoid. We have to draw Amperian loop through this point. First of all, draw a line AB parallel to the magnetic field lines. As it must be closed, we cannot have symmetric Amperian loop in this case. So we choose a rectangular Amperian loop ABCD. By choosing two sides BC and AD perpendicular to the direction of magnetic field, the calculation vanishes and becomes easier. And along the side AB, the line integration vanishes because the magnetic field itself is 0. We can divide the line integration through this closed path in 4 parts across 4 sides of that rectangular Amperian loop. Here, as you can see, just below equation 1, it is divided into 4 parts. Line integration along AB, along BC, along CD, and along DA. Here, the 3 line integrals vanish. How? I will share you mathematically. Okay. The line integration along BC is equal to B to C integration beta dl and is equal to BDL cos 90, because the elemental length dl along BC is vertically upward and direction of magnetic field is towards the left. So the angle between B and DL is 90 degree. As cos 90 is equal to 0, the line integration vanishes along the side BC and similarly along the side DA or AD. Next, along the side CD, the line integration vanishes because the magnetic field B itself is 0 there. So the line integration throughout the closed loop ABCD A is just equal to line integration from A to B. So we can write this. Now integration from A to B is calculated this way. From A to B, dl and the magnetic field B has same direction, so angle between B and dl is 0. So BDL cos 0. And inside the solenoid, B is constant, so we can take it out of integration. And integration A to B dl means summing dl from A to B. That gives the total length of AB, which is small l. Hence, the line integration is equal to B times L. Now, to apply Ampere's circuital law, we must know how much current is enclosed by that Amperian loop. It is just the total number of turns enclosed by that Amperian loop, rectangular loop, and current through a single loop. You know, current through single loop is I, and total number of turns is represented by capital N. And in terms of small n is total number of turns per unit length. So definition would be number of turns per unit length. This implies capital N is equal to small n times L. So we substituted NL in place of capital N. And hence the total current enclosed is NLI. Now, according to Ampere's circuital law, the line integration, which is here equal to BL, must be equal to total current enclosed, which is equal to NLI here. So these two quantities are equal according to Ampere's circuital law. Let's check that line. Okay, that gives you the result. B equal to mu naught small n I. And the result is same as obtained from the Biot-Savart law, but as a special case for infinitely long solenoid. From Biot-Savart law, we can get most general result, which is applicable even for short solenoid in terms of angle. So Ampere's law has limitations, as we can see over here. We get only special case result. Now let's go to next application. This is a toroid. A toroid is a solenoid bent in the form of circular coil. Okay. Now to calculate magnetic field due to this toroid, suppose it has n number of turns, capital N. If you say capital N, it would represent total number of turns in that toroid. And if you write small n, it would be number of turns per unit length of the toroid. The mean radius of this toroid is considered to be A, total number of turns, capital N. The outer radius of the Amperian loop we choose would be R2. I think this is not necessary to mention over here. It will be customary to mention whenever necessary. Let me start. Okay, if current through one loop of toroid is I, then we can apply Ampere's circuital law to three regions around this toroid. To calculate magnetic field at a point in between the center of the toroid and inner radius. Here center of the toroid is this one, inner radius represent this one. In this region, we are going to calculate magnetic field. The first step is to choose the Amperian loop passing through the same field point. Here, the circle of radius R1 is the Amperian loop. This loop does not enclose any current. So the line integral will be equal to mu naught times total current enclosed according to Ampere's Circuital law. As the total current enclosed by this loop is 0, line integral is equal to 0, which implies magnetic field is equal to 0. Okay, now to calculate magnetic field at a point outside the outer radius of the toroid, say at point Q, we draw Amperian circle 3, whose radius is R2. So in this case, net current enclosed by circle 3 would again be 0. I'm saying in this case, the net current enclosed by circle 3 is 0 because the current in the front face is in downward direction, but in the back face, it would be in the upward direction. So net current becomes 0. And similar to this, mathematically, we get the same result for this case also. And this implies magnetic field is 0. So in this case, we have got 0 magnetic field inside the toroid. Inside means here, the region between the center and inner radius of the toroid, the magnetic field is 0. And outside the outer radius, the magnetic field is again 0, as we have proved. Now we are left to calculate magnetic field inside the toroid. That means in between the inner and outer radius of the toroid. Okay. For this case, the Amperian loop is circle of radius A that passes through point S. This Amperian loop encloses total current N times I, where N is the total number of turns in the toroid. And according to Ampere's Circuital law, the line integral B dot dl through that circular loop would be equal to N times I. This is just the statement of Ampere's Circuital law. Yeah, now I'm discussing the third case, that is at a point inside the toroid windings. Okay. I have already mentioned the total magnetic field. Oh, sorry. The line integral of the total magnetic field is equal to mu naught times the total current enclosed. Okay. As the Amperian loop is circle, it is symmetric about the center of the toroid. And the magnetic field at every point of this circle is constant. And the direction of magnetic field and the elemental length dl are along the tangent. They are in the same direction, so angle between them is 0. And now we can take magnetic field B out of the integration sign because it is constant. So we write B integration dl equal to mu naught Ni. Now integration dl throughout this second circle of radius small a would be equal to its circumference. How? Because you are just summing dl, such small pieces of that circular loop throughout the circumference, means you are getting that circumference. So that integration dl is just 2 pi a, and left hand side becomes b into 2 pi a. Right hand is mu naught Ni. So the result is b is equal to mu naught Ni times 2 pi a. Now in terms of small n, b equal to mu naught Ni, where that small n is equal to number of turns, total number of turns divided by circumference of that Amperian circle 2. And that small n is number of turns per unit length of the solenoid. Okay. Yeah, this is all about the applications of Ampere's circuital law. We discussed application in case of straight conductor, in case of long solenoid, and in case of a toroidal windings. Okay, thank you very much.